Hello, my name is Brandon Bob, and today I'll be doing my presentation on delay-tolerant networks. Delay-tolerant networks, DTNs, are designed to function efficiently in adverse conditions and are effective for long-distance communication, such as space communication technology. The conventional internet is ineffective for such environment. DTNs often experience frequent communication disruptions, high error rates for hours or even days. DTNs are designed to overcome such problems, and they can transmit information effectively, thus guaranteeing dependable internet working. DTNs was developed in 2003 to aid communications between space satellites and the Earth. The existing technologies at the time had proven ineffective for space communication, which often involved thousands or even millions of miles. This long distance causes the inevitability of delays, errors, loss of data, and disruptions. Due to the need to enhance communication at an application level, DTNs were introduced. There have been subsequent developments of protocols that integrate some features of DTNs by the Consultative Committee for Space Data Systems. Still, none of them can offer the same flexibility provided by DTNs. The architecture behind DTNs envisions a protocol suite addressing many open issues in networking and extending far beyond the current Internet suite's capability. This presentation discusses the underlying concepts of DTNs, their advantages, disadvantages, and future trends related to them. Delay-tolerant networking is a group of unique protocols that use data stream information, headers adjoined to the data units, to achieve end-to-end information transmissions via network nodes. It fosters the delivery and transmission of data where there are significant disruptions and disconnections, delays, and mismatches in data rate. The architecture is a store and forward communication architecture, where the source nodes transmit DTN bundles via a set network to destination nodes. The protocol works together with an earthbound internet protocol suite. Alternatively, it can function independently without the earthly IP suite. DTN assures data delivery as it uses automatic store and forward techniques. Where possible, all the received data packets are immediately forwarded. Where the forwarding is not presently possible, the data packets are stored and delivered later when the transmission is possible. Consequently, in using DTN, only the subsequent hop should be available. The suitability of using DTN in space communication has proven to be the most significant advantage of this technology. Aside from fundamental service of store and forward internet networking, the technology also offers reliability, security, prioritization, duplicate suppression, remote management, data accounting, in order delivery, and rate buffering. These services are conducted over potential time deposit and a systemic network path. Underlying technology. DTN is an amalgamation of protocols created by the Delay and Disruption Tolerant Networking Research Group, commissioned by the Internet Engineering Task Force. These protocols' versatility is sufficient to either work with earthly IP protocols or work independently. The underlying architecture behind DTN requires bundle storages by nodes for a long time. When the condition allow it, the data packets are immediately forwarded, and where immediate sharing is possible, the node store the data packets to be shared in the future. The store and forward technology is essential for DTN because it ensures data delivery, a feature that is not present in traditional earthly networks such as the internet. As with terrestrial networks, where IP protocols provide transport layer network and service, DTN works in the same way for space communication and information transmission. The data technology compromises a message center and end-to-end overlay described as the bundled layer. Digital devices that use this layer are defined as DTN nodes. This layer is found above the transport layer and below other applications. The technology offers similar functionality as the gateway layer defined in the initial internet design. However, the difference between DTN and ARPANET the internet is that the former is a layer agnostic. It focuses on forwarding virtual messages instead of switching packets. Application areas. The majority of the major application area of DTN is space communication. The conventional internet is ineffective in ensuring effective communication between Earth and space satellites. Initially introduced in 2003, DTN was meant to enhance faster communication between terrestrial networks and space satellites. There is a great distance between Earth and satellites in space, often thousands and even millions of kilometers. Space scientists who deploy satellites to explore outer space depend on DTNs to receive data packets that provide them with a clear picture of the findings of the data collected by the satellites. The abstraction of the communication supplied by the DTN increases its ability to make good decisions related to path selection and scheduling. Aside from space communication, DTNs are also used in earthly applications in shorter distances, shorter than the distance between the Earth and outer space, where there is extreme interference or the error rates are high. Furthermore, where network resources are overburdened, DTNs come into good use as well. DTNs are also used in tactical and military systems to aid communication where the internet and terrestrial networks are ineffective. They're also used in disaster recovery networks, underwater acoustic networks, wildlife monitoring networks, vehicular communication, and the various networks that rely on sensors for communication and data transmission. Now we'll be going over the positives and the negatives. So there are several benefits associated with DTNs. For instance, DTN enables the interoperability of terrestrial space stations and satellites for spacecrafts in outer space. This means that space station scientists on Earth can operate in tandem with the data or information collected by spacecrafts or satellites. Although there are often delays in information sharing, it is not such that it can prevent complete and total miscommunication and data packet delivery. This is the advantage of DTNs over conventional terrestrial internet. Additionally, DTNs offer more effective data transmissions and extensive bandwidth, which can be used for larger data. The collected data from the spacecraft and satellites are often substantially larger, and it requires bandwidth that can support the transmission of this data without significant interruptions. Another positive of DTN is that it offers increased link reliability. There is a higher chance of fewer link disruptions when using DTN for communication between terrestrial space stations and spacecraft. Moreover, DTNs support encryption, integrity checks, and authentication, ensuring increased secure communication. Lastly, DTNs can set priority levels for various datasets, thus improving the quality of service. This ensures that the most important or relevant information is first transmitted to the terrestrial space stations for assessment, and then the rest of the data. Now, in terms of negatives, one of the biggest challenges facing DTNs is their crucial management. The primary security issue is a lack of delay-tolerant technique for the central management. Currently, the technology is at a level where the scientists and authorities responsible for DTN only understand how to use the current schemes, which eventually need an online status essential distribution service, which is impractical in high disruptive environments. The existing available schemes and fundamentally equal to shared secrets or to the exchange public key schemes. This indicates a need for extensive research in this area. Handling replays is a major key challenge for DTNs. There is significant challenge in eliminating the probability of replaying messages or data. Furthermore, there is significant traffic associated with DTNs. Developing a protection strategy for DTNs is a challenge due to their habits of being resource scarce, and there are no generic approaches to address this issue. Additionally, there is a challenge of routing protocol security. The generalization of protocol security for DTNs creates a significant challenge for using the technology for data transmission. Furthermore, there are performance issues related to DTNs. Since they are mostly used for space communication, delays in data packet transmission are an inconvenience to the space scientists and terrestrial space stations. Furthermore, there are relational costs associated with DTNs security, since it comes with computational costs. Now we'll be talking about future trends. Routing protocols are one of the most significant trends in DTN use. It is essential that the user select an appropriate routing protocol that is relevant and appropriate to the information environment. Therefore, space scientists are actively developing routing protocols that will circumvent the challenge associated with delays associated with the DNTs. In disaster situations, communication is often a challenge. As stated earlier, the technology can be used to introduce routing protocols that use techniques that enable and enhance the delivery rate of information and data sets. Developing a protection strategy for DTNs is essential because it helps users to overcome the challenges of scarce resources. Developing generic approaches to address this issue is one of the trends that exist in the innovation and invention of DTN technology. Additionally, there is a challenge of routing protocol security. The generalization of protocol securities for DTN create a significant challenge for using the technology for data transmissions. The collected data from spacecrafts and satellites are often substantially large, and it requires bandwidth that can support the transmissions of this data without significant interruptions. Another positive for DTNs is that it offers increased link reliability. There is a higher chance of fewer link disruptions when using DTNs for communication between terrestrial space stations and spacecrafts. In conclusion, delay-tolerant networks describe networks designed to function efficiently in adverse conditions and are effective for long-distance communication. For instance, space communication technology. DTNs are designed to overcome such problems, and they can transmit information effectively, thus guaranteeing internet working that is dependable. Data delivery is assured by DTN as it uses automatic store and forward techniques. Where possible, all the received data packets are immediately forwarded. Where forwarding is not presently possible, the data packets are stored and forwarded later when transmission is possible. Consequently, in using DTN, it is only the subsequent of hop that should be available. The underlying architecture behind DTN requires bundles storage by nodes for a long time. When the conditions allow it, the data packets are immediately forwarded, and where immediate sharing is impossible, the nodes store the data packets to be shared in the future. The store and forward technology is essential for DTN because it ensures data delivery, a feature that is not present in traditional earthly networks such as the internet. Although there are often delays in information sharing, it is not such that it can prevent complete and total miscommunication and data packet delivery. This is the advantage of DTNs over the conventional terrestrial internet. Thank you for your time, and thank you for listening to my presentation.